All right. Good evening, everyone. Yeah, so I believe most of people have joined. Those who still want to join, try they will find us. Yeah, so uh, my name is Lungo Ferguson. It's right there on the screen in the notes again. So we'll be together in this course for organic chemistry. Uh, and I'm sure you already oriented about organic chemistry, as in being a half course. So I must believe that I'm audible enough. You're able to hear me. So if you can't, please let me know. So organic chemistry, it's part of your basic science that you need to understand in your clinical courses that you need to know before you start doing your clinical years in medicine. So I must believe that in first year you did quite a number of topics. You did quite a number of subtopics in from organic chemistry, just as an introductory part. I'll try to revisit a few so that we can refresh our knowledge together. So I hope my screen is clear enough. And for those who are asking if the meeting is being recorded, yeah, we are recording the meeting. So can you please confirm if you're able to see my screen?
We can see your screen and we can get you.
And am I audible enough?
Yes.
All right, thank you so much. So I must be quick to mention that organic chemistry, it's quite tricky. It's very easy, but due to different reasons, people tend to fail it. Others tend to have challenges with it. But I must assure that it's a very interesting course, and it's very easy if you take it the way you should take it. And how I'm going to take it, organic chemistry is just like mathematics. It's not something that you have to, understand like you are doing physiology, the way maybe the heart muscles pump blood, like all those, you know, electrical impulses, the way they work and everything. For it, it's about rules. You have to understand the rules involved in the reaction. So once you understand the rules, it's just like mathematics. Once you understand the formula, whatever question you are pinned around, no matter how they try to pass the question, you still be able to know that, okay, this question, for me to get the answer, I have to use this formula. For me to get this answer, I have to get I have to use this formula and this formula. So there are rules that you need to understand. And once you understand those rules, it means it will be easier for you to to solve those problems that you'll be given. Yeah. So at some point, we need to use a whiteboard so that you'll be seeing how chemical reactions are taking place. Okay? So you have to show the mechanism of reaction, you have to solve and everything. Otherwise, I'm not sure that if you take it the way you need to take it, it's very, very easy. I can tell that in my second year, organic chemistry was my favorite. Yeah, it was my favorite. Uh, Even my juniors also came just after us. The book that that I was using to solve those problems. I was putting them all the answers in order in manner that everyone could actually be able to use them. And even people that I didn't even know, they could come and approach me to say, "Wow, you helped us a lot. Those notes you were making, those answers you were writing, some of us actually we found them to be very useful." Yeah. Can tell you the other scenario that in when we're writing our final exam for the second part of organic chemistry. In fact, I woke up very late for the exam. I woke up around 8:40 and the exam was at 9 hours. I went there. I was able to write the exam within 1 hour 30 minutes. The exam for 3 hours. I was able to be done. And the minimum I got from all the courses was an A in organic chemistry. Why? Because I had developed a passion in it. And as much as people were saying that organic chemistry is very difficult, organic chemistry makes people repeat courses, what and what in second year. For me, I took it different. I was like, this is time to do things different. So even as for you guys who are from second year, first year going second year, you're going to have seniors who give you, intimidating advice. So don't take every intimidating advice to be something that is going to be as a challenge to you. Everyone has their own, um, personal issues away from academics. So a lot of things affect students in school. It's not just about the bulkness of the courses. But of course, second year, there's a lot of bulk courses like anatomy, physiology, biochemistry. Yeah, especially anatomy. Anatomy is the most bulk. It's more like 3 courses in one. So you really need to use your time wisely. But don't be intimidated. Believe you me, as much as they fail people, not as people fail courses, there will always be people who make it. And I believe you guys will be one of those. So don't be intimidated too much. Say no, second year because of those 250 or so who've passed out of whatever and so on. Yeah, there are a lot of reasons because those guys were not well oriented. They were far away from seniors. They're not given that chance to interact with seniors. As when we were in our third year, seniors were more like our guide. You could go, Doc, what day we did this course in class, this topic in class. So what should I focus on when you study? What should I focus on when studying? Even when you meet during time when you're doing your cooking, you're washing your dishes, your seniors would ask you questions. The more like we call it wearing. They would wire you, ask you questions on topic that you've done to see if you've really understood them. And when you don't really explain very well, your senior would actually help. Say, okay, here you're supposed to say this and this. And you find those same questions that they're asking you, you find them in the test, you find them in the exam. So you actually yes, oh, these questions come. Okay. So in medicine, what we call common things are common. So you have to know common things. You cannot just study everything you find in anatomy. You cannot just study everything you find in Ganong for physiology or Gaiton, whichever book you're using. So you really need guidance. And guidance is what you actually will help you a lot. And we just say, by doing this initiative, we can try by all means to help those who really need to be guided. Okay? Even us, we had people who were before us. We got guidance from them. They tell us, okay, guys, these courses are bulk for you. They're bulk, can't try to you, but they're manageable. And we took that advice to be so that we should open our mind, say, no, in as much as if you might actually fail your first test, tell us, no, if you've never gotten a 40 in your life, you've never gotten a 30 in your life, here at Ridgeway, it will be something common to you. So it's something that they are telling us, say, things here are bad. That's the way when you're in first year or second year, because us second year, we're not doing these courses we're doing. The only course we're doing here was just organic chemistry and biochemistry, that's part of it. But this time around, the courses you guys are doing in third year, you're doing in second year, as we are doing them in third year. That's a difference. Yeah. So that's just a part of advice I'll give you to say, don't be made too much. Do your best where you don't understand. Consult from us, consult from other senior that might be immediate to you. I know may have contact from other seniors. So please use them to your best. Ask where you need guidance, how to prepare for a test, how to go about what and what, because in that you find you're going to have a lot of drama. You have DR, you have labs for storage, you have classes and everything, and those guys they are very fun. So you need to follow the instruction. Yeah. So today we'll just try to review a few basics from organic chemistry, and we'll try to define what about organic chemistry is and why we need to understand this. So basically, organic chemistry, it's just a sub discipline within chemistry. So like you did chemistry was that was just an introductory topic course to chemistry. So a lot of people are majoring in chemistry, they'll do much of it, and they also have to do most of organic chemistry. But for you guys, we're just going to focus on organic chemistry in relation to the human body and other substances that might be used like drugs. Okay, drugs, they have structures that are organic in nature, and those drugs, they interact with our cells in the body. Okay, for example, you take piriton. You know what piriton, when you take it, they say no, it will make you dose. How does it make you dose? So it has a particular shape in which when you take it, it will go and sit on what we call receptors on the cells in our body. And those receptors, depending on the action of the mechanism of the drug, it may either cause chemicals from the cell to go out or go in. They're what we call the chloride, sodium channels, and you understand those in physiology. I don't want to go that way, but I'm just trying to explain why you need to understand this course, because you are going to be doctors, and doctors, you have to understand the human body from what we call the molecular level. Molecular level, you have to know how the cells interact with whatever we take, whether it's food, drinks, chemicals, anything. Okay, because someone might take overdose of Panadol. Okay, and that Panadol can cause actually what we call acetaminophen poisoning. It may cause poisoning, can even kill that person. Okay, but if you don't understand how that Panadol works, you don't explain why someone has died. Okay, so because of the same knowledge of organic chemistry to help you to understand how everything is happening. Okay, why quinine works the way it works, paracetamol, whatever drug you're getting. Yeah, so those drugs, it can be a painkiller. You want to reduce the pain, but it will cause you maybe to sleep, or maybe to induce some nausea. Maybe you are going to have maybe abdominal pains and everything. Those are what we call side effects. So fancy, the drug, instead of just giving you what you want, it also have other effects because it works in other parts of the body. Don't just go direct to where you want it to go. It will go somewhere other parts of the body, and the way those body cells will respond will be different from the other cells. So it might reduce the pain, but also cause you to start vomiting. You see. So because of the interaction, so drug and body interaction is where organic chemistry for medical students in that terms stands. Okay. So like we said, it's a sub-discipline within chemistry, which involves the scientific study of structure, properties, and reactions of organic compounds and materials. Okay. In other terms, it's matter in its various forms that contain carbon atoms. So whatever contains carbon atom is an organic molecule. You did proteins, you did lipids, you did carbohydrates, you did nucleotides or nucleic acids. All those organic compounds. Okay, so they are drugs that work on each and every particular cell. And in that cell, there are molecules that they target. Either they target proteins, either they go there target, you know, nucleic acids. Either they go target, you know, other structures in the body. So these same organic molecules, they interact in different ways. Okay. So we'll try to look at a few families of carbon compounds. And these families would depend on the way these molecules are. So there are molecules that do not have any double bond. There are organic molecules that contains a double bond. There are some that contain a triple bond. So they have different names depending on the functional group they contain. So we'll begin this chapter by introducing the class of compounds and hydrogen that contains carbon and hydrogen, and we shall see how these compounds can be named. Okay, so there are those that end with ane, like alkanes, like methane, butane, propane. All those are alkanes. They don't have any double bond. We'll see as we go. Then there are those that have a double bond. They end with ene as the name. So like butane, it has no double bond. It's an alkane. Then when it has a double bond, it becomes butene. And when it has triple bond, it becomes sorry, when there's a double bond, it is a butene, and when there's triple bond, it becomes butane. So it just depends on how you might pronounce it. So these are what you call the suffix for the names. So we'll see as we go to the nomenclature of carbon compounds, we'll go in detail about them. Okay. So just a brief about hydrocarbons. Like I said, we did proteins, we did carbohydrates, we did lipids, also did nucleic acids in first year. So these are all hydrocarbons. Hydrocarbon, in short, is a compound that contains hydrogen and the carbon molecules, carbon atoms. So I don't know if there are any questions. Let me just check if maybe someone has typed anything. So, like I said, hydrocarbons, these are just organic molecules that contain carbon and hydrogen. Okay. So, for example, this example given here. It's a methane. Methane has only one carbon, and it is bonded to 4 different hydrogen. The other one here, unfortunately, the name is not written. The other one here, it is what we call ethane. Ethane, it's a 2 carbon compound molecule or 2 carbon atom molecule with the 6 hydrogen atoms bonded to these carbon atoms. Okay, so these are what we call hydrocarbons. So you can go as you want. It can be propane, it can be butane, pentane, hexane, depending on the number of carbon. So we'll see as we go how we come up with these names, depending on the number of carbon contained. So that with our alkanes. So like you said, alkanes are hydrocarbons that do not have multiple bonds between carbon atoms. And we can indicate this in the family name and in names for specific compounds by ANE or ane ending. Like I said, methane. Methane does ANE at the end. Okay, so it tells us, say, okay, this is an alkane. And the primary source of alkanes are natural gas and petroleum. The smaller alkanes like methane to butane, these are gases under normal temperature and pressure. And methane is a principal component of natural gas. So methane is found in natural gas. So these compounds, they occur naturally. And we have an example here. So this is propane. So sometimes we use this kind of, actually this is the components we're going to be using. The line kind of drawing for hydrogen for the hydrocarbons. So when you have a compound like this, which has these two lines, so it tells it to say at the end of this line, there's a carbon bonded to 3 hydrogen atoms. In the middle there is a carbon bonded to 2 hydrogen atom. And at the end here again, there's another carbon. Okay. So the
Sir, excuse me, sir.
can you get me? Yes,
Oh, like we can't see the same structures that you're talking about.
but you can see the notes.
Oh, yes, the notes we can see them, but the structures where you're saying to be drawing like, is it like a lion, something like that?
No, a line.
Oh, yeah.
At the end of the notes, you can't see anything like a triangle, like by this one here. Can you see it? If I lost the person.
Which one, sir?
Okay, let me do this.
Oh, yeah, we can now see it.
Um, can you see it now?
Yes, sir.
Okay. So I'm trying to find a pointer that you can use. So meaning when I put it like this, if I put it like this, you can't see the structure no longer visible.
They are now visible, so we can see them.
The problem is you didn't move the slide, so we're just looking at the same slide.
Or the slide has not yet moved.
Mm.
Okay, I'm sorry for that. Yeah, so this is the structure of propane. So propane, it has 3 carbon atoms, okay, which is, let me do this, which is the one here. Can you see my pointer? This red thing I'm trying to move. Can you see it? Can someone confirm, please?
Sir, which one, sir?
Can you see this kind of a red thing I'm moving here? This.
No, sir, we can't see it.
Anyway, I think we'll try to to explain just like that then, but you can still see the structures, right?
Yes.
Yeah, so this is the structure of propane. So like I said, propane, it's a 3-carbon atom. There are 3 carbons. They have carbon here, carbon there, carbon there. And it has no double bonds, meaning it has single bonds throughout. That's why it's called the propane. Okay, propane, which is an alkane. And then you can look at the molecule here, it has all single bonds. These lines, they're all single. Okay. And at the end of each line, there's a carbon. In the middle there's a carbon. So when you draw the line model, at every corner of that zigzag line you write, there's a carbon. And at the end of every line, and at the start of every line, there's a carbon. So this one, if you say, okay, at the end there's a carbon, the middle there's a carbon, the end there's a carbon, it means there'll be 3 carbon atoms in this molecule. That's why it qualifies to be called a propane. And then we have what we call alkenes. I don't know if the slide has moved even there.
No. It hasn't.
Maybe, I don't know if it's a network which is slow.
Okay, now see.
You can see it.
Yes, sir.
Okay. I just need to leave it the way it is like this, because it seems when I put at a full screen, it's not moving fast. Yeah. So alkenes, like we said, they contain at least 1 carbon double bond. So this double bond, it's between 1 carbon and the next carbon. Okay. And this indicated in the family name and in names for specific compounds by an ANE ending. Okay. So alkenes, in short, they have a double bond in them. Okay. So like ethene and propane, the 2 simplest alkenes, are among the most important important industrial chemicals produced in the US. So these mostly they are produced from industries, and you can also find them naturally, like ethane. They say it also occurs in nature as a plant hormone, like in bananas, tomatoes. It's actually one of the most important hormones that is involved in ripening process of the fruits. So those bananas we enjoy, the tomatoes, for them to ripe like that, to become uh, at the stage where you can actually enjoy them as food, it's because of this same molecule that plants produce as hormones to them. Okay, just like even us humans have hormones that control the process in their body. Even plants, they also have chemicals that control the processes. Okay. So this structure you're seeing here, which is a double bond. So you can see the other side, there are 2 lines. The other side, there's 1 line. There's a single line. So it tells us to say this is an alkene. There's a double bond. So at the end of this double bond, there's a carbon. In the mid of the lines, there's a carbon. And on the far end of this single bond or single line, there's also a carbon. So it's a 3-carbon molecule. The previous one was propane because it had single bonds throughout. But this one, because it has a double bond, it's now propene. Okay? I hope you're getting the difference. So because of the double bond contains, it qualifies to be called an alkene. Okay. So these are the major hydrocarbons you find as the families. And then you have what we call the alkynes. So alkynes contain at least one carbon-carbon triple bond. And this is indicated in the family name and in names for specific compounds by a YNE ending. Okay. So these compounds, they have a triple bond. Triple bond means there are 3 bonds between the 2 carbon atoms. Okay. We all know that carbon atom can bond. It has a valence number of 4, isn't it? So that means it can bond to at least 4 other compounds for it to attain actually the the full outermost electron shell. It has to accommodate at least 4, so it can have 8. So because it has a valence of 4, it means it can make the maximum number of 4 bonds. Okay, that's why finally a carbon can have 3 bonds between itself, and then it means each carbon each carbon that is involved in the triple bond won't remain with one valence electron, which can be used to bond with another. That's why you find in propane, like this molecule down here, the carbon at the far end this side, it's only bonded to one hydrogen, cannot bond to any other hydrogen because 3 of its valence electrons have been used to make a triple bond between the 2 carbons that are involved here. Okay. So the 2 examples of alkynes among thousands have a biosynthetic origin are capryl which is an antifungal agent, and the dactyl, a marine natural product that is an inhibitor of pentobarbital metabolism. So these are some kind of naturally occurring molecules. Okay, like this one, the captain they're talking about here, it's an antifungal agent. Antifungal agent, these are just like bacteria agents. These are like microbial agents that actually can cause diseases in the human body. And this one, this molecule, actually, when it is used as a drug, it to actually kill those fungal agents, and it can be used as a drug. Okay, so these are just more like some kind of common naturally occurring molecules which are organic in nature. Okay, like this one, they're saying ethynyl estradiol is a synthetic alkyne whose estrogen-like properties have found use in oral contraceptives. So we all know the contraceptives, like the birth control pills. Okay, they are in different forms, they work different, and because these are organic molecules, some they are used to mimic like hormones. Okay, others can be manufactured, others are produced like natural, just like that. So all these are examples of organic molecules that are occurring naturally. Okay, so this one we are talking about down here, it's propane. Propane is a 3 carbon atom with a triple bond between 2 carbon bond. Okay, so we can start for the alkane. For the alkanes, we said we had the propane, which is a 3 carbon atom or 3 carbon molecule with single bonds. And then we had the propene, which is a 3 carbon molecule with a double bond. And then we had we have a propane now here, which has 3 carbon which is a 3 carbon molecule with a triple bond. So the names just changed because of the number of bonds that are involved in the molecule. If a molecule contains any single bond, it becomes so it contains any double bond, becomes a propane. If it contains n triple bond, it becomes a propyne. If it has single bonds throughout, then it qualifies to be an alkane. Sorry, these sides are not moving. Okay, and then we have what we call aromatic compounds. So aromatic compounds, simply these are compounds that contain a special type of ring. The most common example of which is a benzene ring. There's no special ending for the general family of aromatic compounds. So the compound known as benzene is a prototypical aromatic compound. Like benzene can be written as 6-numbered ring with an alternating single double bond called the Kekule structure. So the structure you're seeing down here, this is the structure of benzene. So a benzene ring has 6 carbon. It's a 6-carbon molecule, which is designed in a ring structure, and it has alternating double bonds inside. So it can be written like the first structure you can see here, where it has a double bond there, a double bond here, a double bond there. I hope you can see the structure I'm talking about. Or you can draw it like the one in the middle, where it's a 6 carbon ring with a circle inside. This circle to say no, because these carbons, they are what we call the sp2 hybridized compounds or atoms. Okay. Some people are saying they're still waiting for the link. I don't know if there are people who are still waiting to be admitted in here. Just a minute. Okay, I can see people who are still waiting. Okay, so I believe those who couldn't make it, so I'm seeing these messages. Okay, I don't know if there's these people who wanted to join. They are still waiting. I can't see them in the waiting room. Okay. And these people, they will just disturb us because we are limited time. and we still have a lot to cover. The good part is that the class is being recorded, so they will be able to access it. I hope I'm still audible. Hello, can you confirm I'm still audible? All right, thank you. So someone has confirmed. Yeah, so like I was saying, these aromatic compounds, we'll understand them in detail. For now, it's just a review of knowing like the family of organic compounds. So understand how these different compounds actually behave. So we have alkanes, we have alkenes, we have alkynes, and then we have aromatic compounds. So these compounds on their own, they have different ways the way they react. So fact, because an alkane, it is saturated in other terms. Like you talked about the saturated lipids where they have no double bonds. So you cannot add anything to it. You cannot add any hydrogen to it. But those like alkenes and the alkynes, because of those double bonds they contain, meaning those carbons, they still have room to accept more hydrogen. So they are unsaturated. So they react different from these ones. Okay. So aromatic compounds, generally we speaking compounds such as alkanes, whose molecules contain only single bonds are referred to as the saturated compound. Like from explaining, say they are saturated because they cannot allow in hydrogen. So because these compounds contain the maximum number of hydrogen atoms that the carbon compounds can possess. Okay, like methane can only accept 4 hydrogen atoms. It is a single carbon atom molecule. So it can only accept 4. That's the maximum. You cannot add anything. But those compounds, like alkenes, alkynes, and aromatic hydrocarbons, they are called unsaturated. Why? Because they possess fewer than the maximum number of hydrogen atoms, and they are capable of reacting with hydrogen and under the proper conditions. So, like we talked about in lipids, say no, you can nautical hydrogenation. Okay, hydrogenation is where you introduce hydrogen to the unsaturated compound so that you add hydrogen to that. So you're changing that molecule from where it was, if it was an alkene, you are changing it into an alkane. Okay, that's a process of hydrogenation. I think if you remember very well, we talked about it in biology. We were talking about lipids. Yeah. So basically, the point here was about the unsaturated and saturated compounds. And then the benzene, based on the principle of resonance theory, recognize that benzene cannot be represented adequately by either structure, but that instead it should be visualized as a hybrid of the two structures. So cannot say this is the only structure like here. I'm sure you can see this structure, the first structure of benzene with these double bonds inside. We can also draw it like this, the one in the middle here. That's why we have this double arrow. So that you can either draw it this way, you can also draw it this way. That's why at the end of the day we say the resonance hybrid structure of benzene, it's where you draw a 6-membered ring, carbon ring with a circle inside. A circle shows that there are double bonds inside. And these double bonds are not localized. In short, they are resonating. They can either be at this point, they can either be at this point, they can be at this point. Okay. So this is the hybrid structure of benzene. So if they ask you to draw the The hybrid structure of benzene, this is the one where you draw a six-membered carbon molecule with a circle inside. And then the CHE structure are these ones. Okay. So basically those are let's respond. Okay. Yeah. So basically those are the families or the groups of hydrogen or hydrocarbons you can find in nature. So alkanes, alkenes, alkynes, and aromatic compounds. And then now go to look at the functional groups. You have to understand what is a functional group and what different types of functional groups you find in organic chemistry. So a functional group, in simple terms, it's a part of a molecule that is involved in a chemical reaction. So two chemicals, they meet together, like we talked about, the formation of those lipids. Okay, so you have those fat acids. Okay, and then we have glycerol. If you remember very well in biology, we talked about that. Glycerol, it's more like a multiple alcohol molecule. Those alcohol, the OH groups, are what we call the functional groups because they are involved, they're the one involved in a chemical reaction. And then when we go to fat acids, we have those COOH group, the carboxylic groups. Those are also functional groups because they are the ones involved in chemical reactions. So when those two react, okay, they will bring about a product, which is a lipid, okay, with those ester bonds. So from this definition saying, so functional groups are common and specific arrangements of atoms that impart predictable reactivity and properties of a molecule. So you can tell how a molecule will react depending on the functional group they contain. So the functional group of an alkene, for example, is its carbon-carbon double bond. So we saw the structure of an alkene. Okay, so I can say that an alkene, it is any hydrocarbon that has a double bond. That double bond is between a carbon and another carbon. No, not like a carbon and an oxygen. No, that's not an alkene. It changes the name because that now it becomes a ketone. Okay, I'm sure I remember in from the carbohydrates, those aldehydes and ketoses, the way those structures were. So the alkenes, we look at those bonds between two carbon atoms. So if there's a double bond between those two carbon atoms, it becomes an alkene. And that double bond, it's what qualifies to be a functional group because a reaction will take place at that point. And then the functional group of alkyne, it's a carbon-carbon triple bond. So those bonds between two carbons, there are three bonds, becomes a functional group. And then alkanes do not have a functional group. Their molecules have carbon-carbon single bonds and carbon-hydrogen bonds. But these bonds are present in molecules of almost all organic compounds. And carbon-carbon single bonds or carbon-hydrogen bonds are in general much less reactive than common functional groups. So in other terms, alkanes are non-reactive. Alkanes are non-reactive because they don't contain any functional group that can undergo a chemical reaction. If they have to undergo a reaction, it means they must undergo collide with a very strong functional group of the different molecule. So they don't have any functional group because, like we said, these are saturated compounds, so they cannot add anything to it, to the carbons involved. So other common functional groups and their properties will be introduced later. So for now, we just talked about the alkenes and the alkynes as the functional group. And the definition, by definition, the functional group, it's the part of a molecule that is directly involved in chemical reaction. So frankly, some molecules actually will have more than one functional group. So will depend on the reactivity of that functional group, as in which direction a molecule will go. Whether this molecule should be an alcohol or an aldehyde, like the way you saw from carbohydrates. So we said, okay, they contain the hydroxyl groups, but they don't qualify to be alcohols because they contain an aldehyde group, which is more reactive than those hydroxyl groups. I thought the most reactive functional group takes the name of the molecule. So we'll see all this as we go. But now we're just trying to get to familiarize ourselves with these fun things. So we have also what we call the alkyl groups. So alkyl groups, an alkyl group, it's any alkane that has lost a hydrogen. Okay. So like we have methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane, as and so on. Once a methane has lost a hydrogen, instead of having 4 hydrogen atoms bonding to the carbon, it let's say it has 3 hydrogen. It's no longer a methane. It becomes an alkyl group. It has lost a hydrogen, and even the name will no longer be a methane. It will become methyl. Okay. So like we said here, they are groups that. So alkyl groups are the groups that we identify for purposes of naming compounds. They are groups that would be obtained by removing a hydrogen atom from an alkane. Okay. And we usually symbolize them with the symbol R. So in the box here, the table below, I hope you guys can see the table. There are different alkane molecules. Can you see the table?
No, sir.
I don't know why this is so slow. Can you see it now?
Yes.
Yes.
Okay, I think maybe this way, that's the best to present. So this table has different alkane molecules. Like here we have methane. Methane, the molecular formula is here CH4, meaning there's 1 carbon and 4 hydrogen atoms. Structural formula, this is structural formula. If to write the structural formula, it means the depends on the molecule. You can write them differently. I'm sure we'll see as we go down with those with most number of carbon atoms. So when methane we remove a hydrogen from a methane, the molecular formula becomes CH3, and the name of an alkyl group produced to become methyl. Okay, so it's just removing the ANE at the end, then you put the YL. That's how you change the names. Like we have ethane, it's C2H8. Sorry, is it C2? Should be H6, this one. Yeah, H6, because each carbon only be bonded to 3 hydrogen atoms. It's not that clear though. Yeah. But this table can still find it in Solomon, the book that we will be using, especially 12th edition, because I was getting them actually direct from that book. But I didn't want to use things that are from the net. I want that you'll be familiar with when you're studying, because if your lecture, I'll be getting direct from the same. Yeah. So propane It's a 3-carbon molecule. You can see the molecular formula is CH3H8. Sorry, C3H8. So meaning there are 3 carbon atoms and 8 hydrogen atoms. And when we talk about the structural formula, it means it becomes CH3, CH2, CH3. So what do we mean by this? It means the first carbon, it means the first carbon is bonded to 3 hydrogen atoms. The second carbon is bonded to 2 hydrogen atoms. The third carbon is bonded to 3 hydrogen atoms. That's what we call by the structural formula. And when you remove one hydrogen, okay, we remove one hydrogen at the end of this molecule, it becomes propyl, okay? It becomes propyl. Well, pronunciations might differ, but yeah, you always meet at the spelling, so it becomes propyl. Propyl, it means it was a propane which has lost one hydrogen, or it was a propane, it's a propane with one less hydrogen, so it becomes propyl. So it's just removing the ANE at the end of that alkane, and then you add the YL. That becomes the molecule. And then you have like kind of hexane, which is the molecule with 6 carbon atoms. So C6H, I don't know how many. Yeah, 12 or whatever. 16. Yeah, somewhere like that. So the structural formula, it's here, it's CH3. It means the first carbon is bonded to 3 hydrogen atoms. The second and the third, actually, and the fourth, they will be carbon bonded to 2 hydrogen atoms, and then the last one bonded to 3 hydrogen atoms. So the structural formula is CH2, then in brackets CH2, another bracket, then in 4. So meaning this 4 outside here, outside the brackets, trying to say that there are 4 carbon atoms bonded to 2 hydrogen atoms each in the molecule, and the far end ones, each one is bonded to 3 hydrogen atoms. Since it was a hexane, if it has lost one hydrogen, it becomes hexyl. Okay, that's how it goes. I don't know if there are people who are trying to join. Okay, like enough. They are now able to join. People are saying they can't get me. Can you get me now?
Yes.
Okay, thank you. Okay, let's try to remove.
Can you kindly increase your make the slides to be full?
Yeah, now the problem is it's very slow when moving the slide. So some tables they don't show once we move the slide. That's why I'm trying to reduce the screen. All right. Thanks for those who've joined. So we're now looking at the alkyl groups. So we've looked at the families of hydrocarbons, which includes alkanes with hydrogen carbons, hydrocarbons with only single bonds. We looked at alkenes, those hydrocarbons with double bond. We looked at uh, alkynes, those hydrocarbons with triple bonds. We looked at aromatic compounds, those compounds with like with a ring structure, and double bonds like benzene ring, this which is the most common structure you'll find. So we also looked at the definition of functional groups. We looked at a few functional groups, but to look at more as we go. We also just looked at alkenes and alkynes as the functional group, and we define that functional group. Functional group is a molecule that is directly involved in a chemical reaction. And we say that alkanes, they do not have a functional group. As a result, they're less reactive. That's why they, in short, they are non-reactive, so they cannot really undergo a chemical reaction, and they are saturated because they contain all all the carbon atoms in the alkanes. They are free bonded to hydrogen and the other carbon atoms, so they cannot accept another molecule, unlike the alkenes and alkynes, which are unsaturated. And I'm sure you can refer back to the knowledge you have from lipids. Talked about the saturated and the unsaturated fatty acids. So it's some kind of same concept. Okay. So can you see this? I don't know if a diagram or whatever it is here.
Yes.
Can you see this one talking about the alkyl groups?
Yes.
Yeah. So this just trying to talk about what we talked about in the previous slide, where we're talking about the alkenes with less one less hydrogen, or in short, alkyl groups. Like we said, alkyl groups is any alkane which has one less hydrogen. Okay. So these alkyl groups, some they are more like a group which is going to a larger alkane. So it has a half, it has a one less hydrogen. So these, we need to understand them for the sake of naming compounds, because find they are compounds that are branched and they are compounds that are not branched. And those which are branched, every single group or every single group branch, you have to take account for it when you're naming a molecule. So that if I give you a name of a molecule, you're able to actually draw a structure for me. If I give you a structure of a molecule, you're able to give me a name for that particular structure. So like, for example, here we have this column for alkane, and then you have the column for alkyl groups. Then here you have the abbreviation that you'll find when you're naming this same molecule, and then you have the bond line structure, the way it looks like, and the model. So the most important here is the way we're coming up with the names. For example, we have methane. Methane is the methane structure where we have a CH3 and a hydrogen. So it's more like a carbon bonded to 4 hydrogen atoms. But methyl, it's a carbon that is bonded to 3 hydrogens, and then it can be bonded to any other molecule this side, but it has one less hydrogen, in short. So this becomes methyl or methyl, whichever way you want to pronounce. And then we have ethane or ethane, whatever way you pronounce. It's a 2-carbon molecule with 6 hydrogen atoms, but when it has one less hydrogen, it becomes ethyl, okay, or ethyl. Then you have propane, which are 3 hydrogen carbon atoms. When it has one less hydrogen, it becomes propyl. You can see the structures here the way they are. Methyl, it's just one line. And then ethyl, it's 2 lines because there are 2 carbons. So at the end of this line, there's a carbon, and at the corner there's a carbon, or whatever we call it, it's a kink of the zigzag line. And then these small lines we are trying to draw here, this zigzag line, we're trying to show it. This is more like a group bonded to any other molecule. So it can be bonded to any other molecule. That's why we're not showing anything here. It's just a group which bonded to a larger molecule. So that group, the way we name it, So the way you name it according to the number of carbon atoms it contains. Sorry about that. Then we can have propane. When it has one less, it becomes propyl. Butane becomes butyl, just like that. And the structures are like here. So we'll see why we need to know this as we go, because we're talking about the nomenclature of these, the IUPAC system of naming organic compounds. These all be accounted for. So while only one alkyl group can be derived from methane or ethane, the methyl and ethyl groups, respectively, two groups can be derived from propane. Okay, so methane can only give us one alkyl group because it can only remove one hydrogen from that carbon, because methane has only one carbon. Then ethane has two carbon atoms. So if you remove from this carbon, you remove the hydrogen, it should be ethyl. You remove that from the other side, it will still be ethyl. But for propane has three carbon atoms. When you remove a hydrogen from the terminal carbons, it becomes propyl. Okay, but if you remove a hydrogen from the carbon atom which is in the middle, it becomes the isopropyl. Okay, so I will say that the removal of the hydrogen from one of the end carbon atoms gives a group that is called the propyl group. Removal of the hydrogen from the middle carbon atom gives a group that is called the isopropyl group. Okay, and then the symbol R is used as a general symbol to represent an N-alkyl group. For example, R might be a methyl group, can be an ethyl group, propyl group, or an isopropyl. So R just a structure that is, it's more like a symbolic structure that you might use to show that, okay, there's an alkyl group this side. Okay, so we say that no, one methane becomes methyl from, like you can see from this diagram down there. Methyl, it's a methane which has lost one hydrogen. Ethyl, it's an ethane with
Excuse me,
one
sir.
less hydrogen. Excuse me?
I can't see the diagram you're talking about.
Can you see it now down there?
Yes, yes, now I can.
Okay. Okay. I think we're doing
Is it
that.
possible if you can just increase the font on your PC without putting it to be full screen?
Mm, let me try to do that. I think unfortunately, let me see. How about now?
Still small. Can you increase again?
Mm, unfortunately. I might need an assistant for that. I'm unable to do that, doc.
Just on that line which is just below, yes.
Now, if I do this, okay.
Wait, what did you say was the problem at first? The slides were not moving.
They were not able to see the diagrams that are down there.
Oh, so what you do is, well, you should present the whole screen. You should present the entire screen, and not the tab or just the other thing. I forgot it. Present the entire
The
screen.
window. Okay, let me do this then.
Don't present using the window. It always does that. Present the whole screen.
So how is it now?
Okay, I'll tell you when it has started.
It's not yet presenting.
It doesn't get started.
Okay. Even now you can't see my screen.
No, just go on the present now, then where it says your entire screen, when you press that,
Yeah, that's what I did actually. I'm always presenting my entire screen.
okay, when you have to you have to click on the entire screen, then share. If you haven't done that, just edit on share your screen.
Okay.
So you have to press on that screen, then the share button will show up, then you can now start sharing.
Okay. I'm sure you can see it now.
Yes, that's it. So now it's sharing the entire screen. You can go to the PowerPoint.
Okay.
Yes.
Can you see everything?
Yes, now we can see everything.
Okay, so down there, that's a small table we're talking about. So we're talking about the presentation of the alkyl groups. So we said they give been decided by the letter R. So like methyl, ethyl, propyl, and isopropyl they can all be presented by same R. I hope I'm still audible. Am I still audible?
Yes, you are.
Yes, I can get you.
Okay, thank you. These network thingy sometimes they perform. Okay, so we also have what we call the phenyl groups and the benzyl groups. Okay, so these are basically the aromatic compounds, like we saw earlier, which are, you know, compound with a benzene ring. Okay, so when a benzene ring is attached to some other group of atoms in a molecule, it is called a phenyl group, and it is represented by it in several ways. Sorry, it's represented in several ways. So, like we saw that a methane, a propane or ethane that is directly attached to maybe a larger group. It means that ethane or propane has lost one hydrogen, or it has one less hydrogen. So it becomes a branch of that larger molecule, and it is called an alkyl group. So the same thing for the benzene rings that are attached to some other group or group of atoms in a molecule. They are, instead of being called like a benzene, they are called the phenyl group. So these are also important when it comes to naming structures. So you can see this structure here, the benzene ring. You can also draw it like this. You can write it like that, where you can write the C6 5 H5. Sorry, it means instead of having 6 hydrogen, it has 5, so it has one less. So it becomes a phenyl group. Okay. So ways of representing a phenyl group. So the combination of a phenyl group and a methylene group is called a benzyl group. Sorry, I've combined the two information here. So these structures are written here on top, where you have an organic molecule or a ring with the double bonds inside, or with a ring inside. These are different ways that you can present a phenyl group. Just like how we presented these structures: the methyl, the ethyl, the propyl, and the butyl, where they are bound to some other structure. Okay. So for the benzene ring structures, they become phenyl groups. Okay. And then the combination of a phenyl group and a methylene group. Methylene group is more like a CH2 molecule that is bonded to. So that it's a methylene group is a CH2 molecule, and this molecule, when it's bonded to the benzene group and to some other group of atoms in a molecule, it becomes a benzyl group. Okay, benzyl, it means it's a benzene structure which is bonded to a methylene group, and as a whole, this group is bonded to some larger molecule. Okay, so it can be a larger molecule, it can be a functional group, depending on whatever it's bonded to. So the structure itself, it becomes a benzyl group. So you have to know the difference between a phenyl group and a benzyl group. Okay, so these are different ways of representing a benzyl group. And then we also try to just familiarize ourselves about the alkyl halides, what we call the haloalkanes. So the halides, these are compounds or the atoms that are found in the group. This group 7 of the periodic table. Those the chlorine, fluorine, bromine, whatever, iodine. So when an alkane is bonded to a halide atom, it becomes an alkyl halide. Alkyl because it has one less hydrogen. Halide because that hydrogen been replaced by a halide. Okay. So alkyl halides are compounds in which a halogen atom, like fluorine, chlorine, bromine, or iodine, replaces a hydrogen atom of an alkane. So, for example, this one, which is supposed to be methane. Methane, we said when you remove one hydrogen, it becomes methyl. And then we replace that hydrogen by a chlorine, becomes methyl chloride. Okay, becomes methyl chloride. That's why like alkyl halide. Okay, so it becomes methyl chloride. And then when an ethane has been replaced, let's say by bromine, becomes ethyl bromide. Okay, so they are all alkyl halides, and alkyl halides are also called the alkanes. Alkanes, simply the generic formula for an alkyl halide is Rx. So R it's representing an alkyl group, then X is representing a halide atom. So where X it's can be fluorine, bromine, or iodine. Okay. So we can either call them as alkyl halides like methyl bromide, maybe propyl chloride, just like that, or can call them as haloalkanes. Haloalkanes, that's more like chloromethane. Instead of saying methyl chloride, you can also call it chloromethane. Okay, maybe bromoethane. That is now the other way you can name them. So we'll see this in detail. It's just more like an overview of how these molecules are called. So alkyl halides are classified as being primary, secondary, or tertiary. So what do you mean by this? So this classification is based on the carbon atom to which the halogen is directly attached. So this was also part of the introductory, part of the introductory to organic chemistry you had in first year, where you need to understand how to classify carbon atoms and hydrogen atoms in a molecule. So if the carbon atom that bears the halogen is directly attached to only one other carbon, the carbon atom is said to be a primary carbon atom. And the alkyl halide is classified as a primary alkyl halide. So I think I had the structure here. How we come about the primary, the secondary, and the tertiary. Okay. So like this carbon is bonded to only one carbon next to it. So it is called a primary carbon. So primary carbon, we write one with a, what do you call it? It's more like a symbol of a degree on top there. So it's called a primary. Secondary is 2 with a power 0 on top there, which is more like, I don't know how to call it, like a degree or whatever. So it's called a secondary carbon when a carbon is bonded to 2 other carbon atoms. Then when a carbon is bonded to 3 other carbon atoms, because it becomes a tertiary. Okay, when it is bonded to 4, it becomes a quaternary, just like that. That's how it goes. So same applies to the halogens. So to the alkyl halides, an alkyl halide that has where a halogen is bonded to the primary carbon, it becomes a primary alkyl halide. When a halogen is bonded to a secondary carbon, like this structure in the middle here, this carbon, the one in blue, is bonded to 2 other carbon atoms. So it qualifies to become a secondary carbon. And because the chlorine molecule or atom is bonded to this same secondary carbon, the whole molecule is called a secondary alkyl halide. It also goes to the one which is at the last structure here. This carbon, the one in blue, it's bonded to 3 other carbon atoms. So because of that, it becomes a tertiary carbon, and the whole molecule becomes a tertiary alkyl halide because this chlorine is bonded to the tertiary carbon. So if this chlorine was bonded to this one of these other carbon atoms which are going to this tertiary carbon, it would become a primary, because each of these carbon is bonded to this one, which is in blue. So just depending on the location of the carbon, which is bonded direct to the halogen, is where you can figure out whether it's a primary or secondary. So, like the information here is saying, if the carbon that bears the halogen is itself directly attached to other carbon atoms, to two other carbon atoms, then the carbon is secondary carbon, and the alkyl halide is secondary alkyl halide. If the carbon atom bears the halogen is directly attached to three other carbon atoms, then the carbon is tertiary carbon, and the alkyl halide is a tertiary alkyl halide. Okay. So these were the examples being talked about. And then we have it's the continuation of the other part. So an alkyl halide is a compound with a halogen atom bonded to an alkene carbon. In order nomenclature, such compounds were sometimes referred to as vinyl halides. So an alkene, we say it's a compound that has a double bond in it. And when this compound has a halogen bonded to one of their carbons, it becomes an alkyl halide. And then you have what we call the aryl halide, which is a compound with a halogen atom bonded to an aromatic ring, such as benzene ring. Okay. So all these are just ways of classifying these molecules. Like when you tell me to say, okay, this is chloromethane, this is chlorobutane, this is iodopropane, must be able to know what class that molecule belongs to, what functional groups are involved, and the like. Okay, so these are on the alkanes or the alkyl halides. So these were the structures for the alkyl chloride. Alkyl chloride is more like an alkene that is bonded, that has a chloride in it. And then a phenyl bromide. Phenyl, we said it's it's a benzene ring that is bonded to some other structure. So like this benzene benzene ring is bonded to a bromine, so it becomes a phenyl bromide. Okay. No, I mean we still have where to go. So there are some examples you might want to try yourself. So there's also an explanation there about how the answer comes about, just for you to test your understanding as you devise the notes. So let's try to look at the alcohols and phenols. These are also other functional groups, like we talked about. Say functional groups, so these are groups that are involved in chemical reaction. So like methyl alcohol, also called the methanol, has the structural formula of CH3OH. So, and is the simplest member of a family of organic compounds known as alcohols. So alcohols, these are compounds that contain a hydroxyl group. Okay, so the characteristic functional group of this family is the hydroxyl group attached to the sp3 hybridized carbon atom. So I won't talk much about the hybridization because one focus there, but this was some part of the information you need to actually get in your introductory part of organic chemistry. So can't really like exhaust everything, but the hybridization part of the carbon comes as out of the way the electrons actually are organized in those electron shells. So our main focus is on the functional group for now. So like we said, an alcohol is an organic molecule that has a hydroxyl group. Okay. So like I said, those like the glucose, the galactose you talked about in biology, those they had multiple hydroxyl groups. So they had multiple alcohol groups. But because of the functional group that they contained that they had, which were more reactive than the hydroxyl group, they were called maybe the ketones or the aldehydes because of the high reactive molecule, the functional group they contained. Otherwise, an alcohol is any molecule, an organic compound that has a hydroxyl group. Another example is ethyl alcohol or ethanol. So we'll see how we come about with the names as we go to the nomenclature. So alcohols may be viewed structurally in two ways: as a hydroxyl derivative of an alkane or an alkyl derivative of water. So they can come from any other point. So ethyl alcohol, for example, can be seen as an ethane molecule in which one hydrogen has been replaced by a hydroxyl group, or can be seen as a water molecule in which one hydrogen has been replaced by an ethyl group. So this diagram here is trying to show us how this can be derivated. So we have propane, ethane here, which is a 2 carbon atom molecule, and one hydrogen. If one hydrogen has been replaced by a hydroxyl group, it becomes ethyl alcohol or ethanol. Okay, and then if you have water and one hydrogen has been replaced by an ethyl group, ethyl group is an ethane that has lost hydrogen, it becomes still becomes an ethanol. So meaning it's a water which has been in which hydrogen has been replaced by an ethyl group. So it can be in two ways. Yeah. So as with alkyl halides, alcohols are classified into three groups, just like we classified the alkyl halides. So you have the secondary, tertiary, and the primary. So you have the primary, secondary, and tertiary. So this classification is based on the degree of substitution of the carbon to which the hydroxyl group is directly attached. So if the carbon has only one other carbon attached to it, the carbon is said to be a primary carbon and the alcohol is primary alcohol, just like we had for the halides. So when the carbon that is bonded to that particular group, which is the hydroxyl group, is bonded to only one other carbon, it is a primary carbon. Therefore, the alcohol will be primary alcohol. It will be the same for the secondary and the tertiary. So if the carbon atom that bears the hydroxyl group also has two other carbon atoms attached to it, this carbon is called the secondary carbon, and the alcohol will be secondary alcohol. So we have these examples here. So like I explained earlier, this is something that you can read from the other information that we had. Same applies to the tertiary alcohol. So when a hydroxyl group is bonded to a benzene ring, the combination of the ring and the hydroxyl group is called a phenol. So we had a phenyl group, which is a benzene ring bonded to any other group. Now, this benzene ring, if it's bonded to a halogen, it becomes a phenyl halide, or like we had the phenyl bromide. But when this same benzene ring is bonded to the hydroxyl group, it becomes a phenol. Okay. So phenols differ significantly from alcohol in terms of their relative acidity, and thus they are considered a distinct functional group. So their reactivity would differ from the way most alcohols react because of the acidic nature of the molecule. That's what we are trying to explain here. So they are an alcohol group, but their reactivity it's different from the normal alcohols. Okay, because of the arrangement of bonds in which this molecule is, this functional group is attached. So like this structure is called, it's a phenol found in thiam, which is thymol. Then you have estradiol, which is a sex hormone that contains both alcohol and phenol groups. Then you have tetracycline, which is an antibiotic containing a phenol group. This one, the far end. So, like I said, that you guys, you become doctors, you start learning about drugs. It's funny, some of these drugs, they have funny structures that would be very beneficial if they are used because of the way they react with our receptors in the cells of the cells. And then we have ethers. I don't know if that is a question or it's a okay.
Emmanuel, you can unmute yourself and speak.
Yeah, I just wanted to ask for those like estradiol and all that, are we supposed to master them or maybe, yeah.
Or these structures. No. I'm just trying to make you appreciate that these actually they are structures that are occurring naturally. Some are hormones, like we said, the estradiol, which is a sex hormone. You don't really need to master this. It's just a structure trinity. It's an organic molecule that occurs actually naturally in our bodies, and it's very very important that we understand this course. Our focus will be on how the chemical reaction takes place. So you did need to know how mechanisms of the action takes place. But for these structures, no, you don't really need to master them.
Right.
Okay. So for now, we're just trying to understand these kind of functional groups in general, as in what are they, how they react. We'll see, like each one will be a topic on its own. So we have what we call ethers. Ethers, they have a general formula of an R with a hydrogen, the oxygen in the middle, and a next R. So like you have an alkyl group bonded to an oxygen, and also next to an alkyl group. Okay, so it can be like this structure. The R bonded to oxygen and bonded to the R, or it can be R bonded to oxygen and then bonded to uh, R with the prime. So this prime we've put here, it's simply to say this first alkyl group is different from the other alkyl group. Or it can be same alkyl group on both sides. That's why we have this same R. So in short, it can be, let's say, methyl group bonded to oxygen, and that oxygen is bonded to, and let's say, a propyl group or a methyl group or a butyl group, then just an alkyl group. That's why we're saying where R may be an alkyl group or phenyl group, different from the first R we have, which is an alkyl group. Okay, so we'll see the examples as we go. So ethers can be thought as a derivative of water in which both hydrogen atoms have been replaced by alkyl groups. The bond angle of the oxygen and atom of an ether is ordinary, slightly. I don't know what I did here. Let me do this. Yeah, it's only larger than that of water. Okay, so don't really need to master about the bond angle and everything. Just know that and ethers, they have an alkyl group bonded to a hydrogen and bonded to this. But see, the bond angle is coming as a result of these lone paired electrons, because see, these lone paired electrons, these are orbitals, and these orbitals, they also need enough space for these electrons to rotate. And we know that these bonds also contain electrons, so there is repulsion involved there. So as a result, these bonds they will form an angle which is about 110 degrees. Okay, for this molecule, say the dimethyl ether. So dimethyl ether, it's more like an ether with the methyl groups on both sides. So I would say dimethyl ether. You understand how the names come about as we go. So the functional group, it's the carbon bonded to oxygen and bonded to carbon. Whatever comes later there is it's not really important. It can be a larger molecule, can be just a small molecule, like we have the ether, the methyl group this side. As long as it's an oxygen bonded to two other carbon atoms, okay, it qualifies to be an ether. So these are different examples. So these are just some kind of clinical scenarios where you actually have to appreciate why these organic compounds are important. I'm sure you guys can lead on your own on about that. So that's about ether. So ether is just an alkyl group bonded to hydrogen, oxygen bonded to another alkyl group. So like I said, it's more like can be thought of a derivative of water, where like water, it is oxygen bonded to hydrogen and another hydrogen. But if those hydrogen, both those two hydrogen will be replaced by alkyl groups, it becomes an ether. So instead of having a hydrogen, this side we have a methyl. Instead of having a hydrogen side, maybe we have another methyl, and it becomes this one we're calling as dimethyl. Dimethyl means we have two methyl groups bonded to a hydrogen, an oxygen. So ether, dimethyl ether, like that. When you have amines just as alcohols and ethers may be considered as organic derivatives of water. Amines may be considered as the organic derivatives of ammonia. So you know ammonia is like this, more like nitrogen bonded to three hydrogen atoms. And when one hydrogen has been replaced by one hydrogen has been replaced by an alkyl group, it becomes an amine. So an amine is more like an alkyl group bonded to the the nitrogen, which is also bonded to hydrogen atoms, like this second structure here. I hope you can see it. Okay. So these are some kind of structures of common natural occurring compounds you find, which are amines, like amphetamine, the putrescine, whatever. So amphetamine is more like a dangerous stimulant. Then this one, putrescine, it's more like found in decaying meat. So these are more like natural occurring organic compounds. So amines are classified as primary, secondary, or tertiary amines. This classification is also based on the number of organic groups that are attached to the nitrogen atom. So we can say this kind of classification is a bit different from the one we had, where you look at the carbon atoms, as in how many other carbon atoms are bonded to that particular carbon, which has a functional group. So here we look at nitrogen. So when this nitrogen is bonded to only one alkyl group, it is called a primary amine. When this nitrogen is bonded to two alkyl groups, like we have R here and R prime there, it becomes a secondary amine. When you have this nitrogen bonded to three different alkyl groups, it becomes a tertiary amine. That's just about how you might classify them. So just look at the number of alkyl groups involved. So note that this is quite different from the way alcohols and alkyl halides are classified. So like isopropylamine, for example, is a primary amine, even though it's the amino group is attached to a secondary carbon atom. it is a primary because only one organic compound, organic molecule or organic group is attached to the nitrogen. So what I'm trying to talk about here is this structure here. This structure is that this carbon, which is bonded to a nitrogen, it is bonded to two other carbons. So if this was an alcohol or an alkyl halide, it would have qualified to become a secondary compound. But because this nitrogen is only bonded to one carbon, which is an alkyl group in this place, it still remains as a secondary amine. But this one here, which is more like a ring structure and there's a nitrogen in the middle. So this nitrogen is more likely to be viewed as if it bonded to two different alkyl groups because this bonded to this side and this side, as it becomes uh, a secondary amine, which is a cyclic secondary amine. This molecule called the pyridine, whatever. So it's just about on the issue of classification. So these are other kind of amines you might find like amphetamine, the dopamine, nicotine. These are actually drugs. So like you're saying, amphetamine, it's a powerful dangerous stimulant. It is a primary amine. Dopamine, an important neurotransmitter whose depression is associated with Parkinson's disease. You understand these things as you do other courses. So some of these are drugs. So we found that the organic compounds that must be understood even the way when you are trying to explain the maybe mechanism of action of a drug, you find that there's way these drugs interact with our receptors. Yeah, I'm trying to move with time. Hope we won't go beyond the limit. Yeah, and then we have aldehyde and ketones. These are also functional group. You learn them in biology. So aldehyde and ketones both contain a carbonyl group, a group in which a carbon atom has a double bond to oxygen. So a carbonyl group of an aldehyde is bonded to one hydrogen atom and one carbon atom, except for formaldehyde, which is the only aldehyde bearing two hydrogen atoms. So this is the functional group of carbonyl group. So it's a carbon bonded to then a double bonded to an oxygen atom. Because it's called a carbonyl group. So this group can be bonded to either to an alkyl group and a hydrogen, or to two different alkyl groups. So when it's bonded to an alkyl group and a hydrogen, it is an aldehyde. Try to remember this information from first year. And when it's bonded to two alkyl groups, this carbon which is involved, which is bonded direct to oxygen, when it's bonded to two different alkyl groups, it's called a ketone. Yeah, basically, that information is clear. There's some more explanation you might need. Otherwise, ketones and aldehydes, they have the same functional group. It just depends where that carbon, which is bonded to oxygen, is. So aldehyde, we already know that the functional group is already at the terminal end of the molecule. But for ketones, usually the carbon is in the middle. Yeah. So these are some other examples of aldehyde and ketones you might find occurring naturally, like formaldehyde, acetaldehyde, benzaldehyde. These are all aldehydes. And then you have the ketones like acetone. We have this one, carbon. We have ethyl methyl ketone, whatever. So these are some kind of naturally occurring carbon compounds. Don't really need to master them, just know the functional group. As long as I know the functional group, can identify, okay, this is an aldehyde, this is a ketone, this is an amine, this is an ether, then you are good. Then you have the carboxylic acids, you have esters and amides. These are also similar in nature. So carboxylic acids, remember when you looked at the fat acids, I explained about them where you have the COOH group. This is a carboxylic acid. Then esters were coming, let's say a hydroxyl group reacts with a carboxylic group. They produce an ester bond. I'm sure you remember those. And then you have the amides. So carboxylic acids, esters, and amides all contain a carbonyl group that is bonded to an oxygen or nitrogen atom. So as we shall learn later in chapters, all these functional groups are interconvertible by appropriate chosen reactions. So these reactions can actually they can be converted in two different ways. Like we said, the carboxylic acid reacts with a hydroxyl group, which is an alcohol, to produce an ester, which is an ester bond. So this carboxylic acids have a carbonyl group bonded to a hydroxyl group, and they have a general formula of alkyl group bonded to a carbon, which is that bonded to double bonded to an oxygen, which is more like a carbonyl group, and then there's a hydroxyl group, which is the OH group. Together making the carboxylic group. Then we write as the COOH. So these are examples of carboxylic groups. And the way you can write them, you can either write them like this: RC, the bond to oxygen and hydroxyl group, or like this one, or like this. Different ways you can actually write them. And then these are examples. Formic acid, this is how it is. So formic acid is more like there's only one carbon atom, okay, which is bonded to hydrogen, bonded to oxygen, and a hydroxyl group. Then you have acetic acid, you have benzoic acid. So all these are acids. That's why they're called carboxylic acids. So they have a carboxylic acid group. Then esters have the general formula of the alkyl group bonded to carbon and carbonyl, or the carbonyl group with the no, I can call it more like alkoxyl group. So alkoxyl group is more like an alkyl group which is bonded to an oxygen molecule or atom. So we have the carbonyl group bonded to an alkoxyl group. So these are esters. So like this structure here, we have the alkyl group bonded to carbonyl group and carbonyl group bonded to alkoxyl group. So these are esters. So imagine there was no this oxygen bonded double bond to this carbon, it would have been called an ether. And because of that, it's an ester. So you have to know, don't confuse these functional groups. So just be careful. They might look similar, but you have to pay attention to the differences. That's why they are highlighted here. These are actually the part which defines the functional group. So this is just a general formula. So like this one, which is ethyl acetate, is an important solvent. It's an ester. So like this one, it's methyl butanoate, smell like whatever. So these are all esters, and esters, like we had those phospholipids, those were esters because of the bonds they contain. So esters can be made from carboxylic acid and alcohol through the acid catalyzed loss of molecule of water. So we have an acetate here, we have ethane ethyl alcohol. When they react, in a catalyzed reaction, they will produce ethyl acetate, which is this one, and water. So is it a condensation reaction or a dehydration reaction? So because water is lost, it becomes what do you call it? An elimination reaction or condensation reaction. Yeah, so these are examples of esters. Then you have the amides. Amides have the formula which is written there. So these are different formulas of amides, where a carbonyl group is bonded to a nitrogen atom bearing hydrogen and an alkyl group. So it's more like we had the what were these amines. Now it's just an alkyl group bonded to a nitrogen atom with the two hydrogen atoms. Here we have an alkyl group bonded to a carbonyl group, and this carbonyl group bonded to the amino group. Together they produce an amide. Yeah. So we have different examples. You have like acetamide, you have the N-methyl acetamide. So we know how to name these. So for now, we just know about the functional groups involved. So you can have the N dimethyl. So this means that we have a methyl group, another methyl group going to the same nitrogen. So that's why we have N dimethyl acetamide. So acetamide is more like the whole amide is acetamide with two branched methyl groups. Then we have the nitriles. A nitrile has the formula of alkyl group bonded to carbon, which is triple bonded to a nitrogen. So the carbon and the nitrogen of a nitrile are sp hybridized. So in IUPAC systematic nomenclature, a cyclic nitriles are named by adding the suffix nitrile. So we'll see this as we come to the naming. So nitrile to the name of the corresponding hydrocarbon. So the carbon atom of the nitrile group is assigned carbon number 1. So we'll see why these numbers are coming up. But for now, if you have, what we're trying to say is that if you have a butane alkane that is bonded to a nitrile group, it becomes butane nitrile. So just add nitrile at the end of the molecule. So if it's an ethane, and that ethane, in that ethane we have a nitrile group, it becomes ethane nitrile. You have propane or propene, becomes propene nitrile. So just add nitrile at the end. But for nomenclature, we'll learn later. Otherwise, you just need to know how the nitrile group is, how the amide group is, how the ether group is, how the carbonyl, the aldehyde groups, the carboxylic groups are, and everything. So you can also have the cyclic nitriles, which are named by adding the carbonitrile to the name of the ring system. So like benzene, it becomes benzene carbonitrile, cyclohex carbonitrile, just like that. As long as it's a ring structure, just add that. So this is a summary of all the functional groups we've talked about. So it's a family. It's a summary of important families of organic compounds we've talked about. So we have the alkanes, we have the alkenes, we have the alkynes, we have the aromatic compounds, we have the alkanes, we have the alcohols, we have the phenols, we have the ethers. So they're quite a number. So we have examples, structures, and the IUPAC name, how they are called. So this, we have the amines, we have the aldehyde, we have the ketone, we have carboxylic acid, we have esters, we have amides, we have the nitriles. So this summarizes like everything we have actually covered. Otherwise, I don't know if you have any questions. I don't know if you're able to unmute yourself and ask. Basically, that's what we had for you today. Not take much of your time because actually it's even beyond 2 hours. So, do you have any questions, doctors? Okay, so if we don't have any questions, uh, the 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 class was recorded, so you can feel free to actually to visit the record so that you can try to follow and or let's go on. You can ask a question.
Yeah, thank you, sir. Like for this same function group that you have mentioned, will be throughout the course we'll be talking like each topic, each function group for what? Because you said that you shouldn't master these same examples. What? Because we'll start learning them one by one. So that's my question, sir.
Or I think he the question that he asked about was whether you master those structures. Like we talked about estradiol, those other structures. They are more like complicated structures. I'm sure you'll find some other similar structures in biochemistry where you need to master them. Like let's say when we talk about the amino acids, how they react. You even talk about some other drugs, just a few kind of drugs that you might need to master structures. But for organic chemistry, functional groups will be important because they will tell you about the reaction. They will tell you to predict the reaction, what like product is going to be. Let's say a carboxylic acid is reacting with an alcohol. We know that they're going to produce an ester bond. So even the way the reaction takes place actually depends on the functional group. But for those structures, for the naturally occurring structures I was talking about, like what structures were those? Uh, like yeah, this one should be this one. It's in this structure here, the tetracycline. So this structure, for us, we're going to ask you about this to draw this structure. What? You can only maybe bring a question. How an alcohol actually react with maybe a related molecule. Let's say an alcohol, how does it react with maybe an aldehyde, a carboxylic acid, how it react with an amine, just like that. So what I meant to say, we'll learn topic by topic is when talk about amides, you have to understand what are the properties of amides, how do they react, okay? Talk of nitriles, how do they react? What are their properties? So there is actually the way we actually explain the mechanical reaction, the mechanism of reaction. You have to show how electrons actually attacking each other to form a bond, just like that. But for structures like this, don't have to master them. I don't know if I've answered your question.
Yes, sir.
Okay, anyone else with a question? Okay, so if we don't have questions, we can call it a night. And thank you so much for attending.